smarter impact is about going beyond ourselves, our work, and our communities. It's about enabling better choices that make a difference in people's lives. And recognizing that everything is connected. To make a smarter impact, we must be knowledge-led, human-centric, and optimistic. Ready to make a smarter impact? Talk with our team or visit our website to learn how.
Hi, my name's John Von Buren. I'm Director of Facilities at Oregon Episcopal School in Portland, Oregon, and I'm happy to be with you along with my teammates today to talk to you about success with data-driven design. We'll be talking specifically about a few projects, two of which are here on the OES campus. One, our lower school that we occupied in 2016, and the other, our athletic center, which is currently under construction. I'm here with Steffi and Ruan, and I'll let them introduce themselves. Steffi?
Hi, I'm Steffi Knudsen with Hacker Architects. We're a 60-person firm located here in Portland, Oregon. I've been with the firm for about 10 years, and my role on this project was as principal and project manager. Ruan?
Thanks, Steffi. Hi, everybody. I'm Ruan Jayawira. I'm a mechanical engineer and associate principal at PAE. We're a 300-plus firm here on the West Coast, Seattle, Portland, San Francisco. We're going to talk about multiple schools, like John said, the two projects at the OES campus, plus a few more. By the way, we wanted to mention that at this point, we're hoping to have a Q&A session at the end of this. If there isn't, our emails are on the website under this description of this event. So please feel free to email us with any questions that you may have. We'll be happy to answer your questions through that if we don't have a Q&A session.
We wanted to start this presentation with this slide because we're going to walk through how we use data to drive high performance design over 3 specific projects, but there's actually a longer progression of the team learning that went into these projects. So while we've been improving on naturally ventilated projects over the last decade, this progression really started with PAE's work on an addition to Earl Boyle's elementary school in 2011. This was a 10 classroom addition for pre-K and kindergarten, adding to the existing school for the David Douglas School District. And they wanted to consider some higher energy savings goals than they previously had. And so PAE and the architect, Bora Architects, started with a discussion about a robust envelope and enclosure, and then efficiencies in the mechanical system. The district didn't cool their buildings already, so discussions about active cooling really wasn't an issue. And so they were able to just employ operable windows and ceiling fans to have the kind of comfort that they were used to. But they really wanted to tackle the idea of passive heating. Once they modeled the envelope, they found that they really didn't need much heat, and they were able to use a small dedicated outside air system and just the body heat of the students. And so they did some analyses to prove that that would work. Now, while this project was under construction is when we began working with John and Ruan on the Oregon Episcopal School's new lower school. That program for that school was a little bit more complex than at Earl Boyle's because it had more classrooms, it had a library or learning commons, and it had a dining room, but it was a relatively simple project. The existing campus was used to active cooling, but it was really interested in higher sustainability goals. And so we suggested a similar approach to the passive heating, and then we took a hard look at if and how we could passively cool the building. And we'll go over that data analysis today. Next was, as the lower school was finishing its construction, PAE started on 3 elementary school projects for the Reynolds School District. They're very similar in program to each other, but they were more complex than the lower school project in that they had a cafeteria and a gym, and they were larger. In addition, all 3 were Title I schools with a high percentage of free and reduced lunch, and it was really important to the district to provide a level of equity, both in the programming, but also in the performance of the schools. The district, though, they didn't really know what that meant. And so PAE brought the concept of passive heating and cooling to them, along with some of the lessons that they'd learned from the lower school, and they did some of the same data analysis. But for the district, the teachers union really would not accept a broader temperature range. Their contract specified nothing above 72 degrees. The district for this project was using an owner's rep, so there wasn't the kind of direct connection between the owner and the teachers. And so there was some pretty complex negotiations for that. And so in the end, while they did passively heat and cool the projects, just like the lower school project did, they added on top of that a VRF system to make sure that the temperatures stayed in range. So we're going to talk a little bit about how we make these costs pencil. And for this project, because the VRF was additive rather than a trade-off, the first cost ended up being a little bit higher. It still saved in energy over the long term though. Next on the docket was the French American International School that really happened around the same time that PAE was designing the Reynolds School. This was a private middle school with about 16 classrooms. And again, we used some of the lessons that we learned from the lower school. We knew we could do the same kind of passive heating and cooling, but the site and the building form were quite different for this project. So our natural ventilation approach had to adjust to be much more of a cross ventilation than a stacked ventilation approach. And we'll show you some diagrams about how that worked. But one of the lessons we did learn from the lower school was that we modeled more than just the worst case classroom. We were able to model more of the building so we could see how they perform differently, and we could find more specific solutions. In other words, we didn't have to employ a full building solution to a localized problem. The other thing was that while this project did employ an owner's rep for the technical coordination, they had a highly involved owners group to make the qualitative decisions. And because it was a private school, there was more direct engagement and leeway with the teachers regarding comfort ranges. Almost last but not least, the Lake Ridge Junior High started as the French American School was finishing its design process and the Reynolds School was under construction. This program was more complicated than any of the rest of the projects because it was a junior high school and it had a lot of different kinds of programmatic needs. The administration for Lake Ridge actually toured the lower school with John, and that was instrumental in convincing them that the passive approaches were feasible. Basically, they could meet an owner who was happy. Even so, PAE still did a lot of analyses to show the data. And they were able to use the lower school as an example, both in terms of the data and the results. This district had direct discussions with the principal and the teachers, and so they were able to get buy-in on expanded comfort. This is where it's really important to be able to talk about the differences between temperature and comfort. And these groups were willing to embrace a wider temperature range because they understood that they would still have comfort. And as a result, Lake Ridge was able to eliminate active cooling like the lower school project did. And then last, under construction right now is the athletic center, and we were able to work again with John at the Oregon Episcopal School. Now, this is a completely different program than the other projects in that it's a large athletic center, but it also will be a main hub for campus events for all school gathering. And as a result, not only are we considering high performance energy goals, but also resiliency goals. Just to add to some of the complexity, this is not only an addition, but also a renovation of their existing gym. And so we had to consider that. And we couldn't just repeat the lower school strategies because the program was so different. We had to do new analyses to find some new solutions. Our modeling did show that we can passively heat and cool an athletic center, so that was good. And we learned some really interesting lessons that we think we can apply to some future projects, and we'll go through some of those with you today. Like the lower school, this project is net zero ready, and the existing gym's roof is, while the existing gym's roof was sloped to the north, we ended up sloping the addition to the south so that we could add PV. So a lot of credit for successful projects really has to go to the client. The client, it's their project, and they really set the tone. For projects to be able to get to net zero or net zero ready, clients really need to be able to listen to the design team and to their stakeholders, and sometimes we'll have to bring up some pretty unconventional ideas to try and see what's feasible. A client needs to be interested in improving their energy performance, even when sometimes it might deviate from their building standards or what they've always done. But the client also needs to be willing to voice concerns during the design process, and not necessarily to dictate what solution that will be, but rather to let the team help them find solutions to those concerns, because problem solving is it's what we do. And at the end, the client needs to understand that this will take a little additional design time and modeling time. And as a result, we need to have time in the schedule and in the fee in order to allow that to happen. Now, in order to help the client needs data. We were really fortunate when we were working with OES to work with John, who was very willing to listen to our crazy ideas. But what he asked in return was to see the data. He knew his stakeholders. He knew what kinds of questions that they would be asking, especially when they saw something that wasn't what they expected. And so that really helped us as a design team provide the right data for what he needed in order to get their buy-in, but also in order for him to have comfort that the building will work as we're promising. John was a full participant in the design team, and we cannot stress enough how important that is for getting high performance designs and to get to the right kinds of decisions. The second critical aspect of a team that's going to achieve high performance like net zero is trust. This is a two-way relationship. The owner needs to know that they will get a straightforward answer from the design team and not just something that will further a design agenda. The design team needs to be able to bring half-baked solutions to the owner and trust that the owner will see them as part of an iterative process, and that we're all focused on an end goal, and that we need to be able to bring partial solutions and get partial feedback in order to hone in on the right solution. And again, this just takes some time, and so we need to build that into the project. We don't talk about it enough, but the contractor is the third leg of the stool. It's a critical part of the success of the project. If a project can bring the contractor on board at the very beginning of schematic design or partway through schematic design, it will really allow for a more collaborative process during pre-construction and better feedback on constructability and cost modeling. It also allows the contractor to be on board with the rest of the design team and be a part of our shared goal. But in order for that to happen, the owner and the contractor need to be able to do and be willing to do the additional cost analyses that the team will need as we go through that iterative process. We've also found that if the legal structures allow it, having early subcontractor participation, such as the mechanical, electrical, and plumbing subcontractors, really helps us get the right kind of solution to meet the project's goals. So having those three legs of the stool together, the owner, the design team, and the contractor, for the three projects we're going to talk about today, the two for the Oregon Episcopal School and one for the French American School, we had really good owner participation. PAE and Hacker were the design team for all three of those projects, but we had three different contractors, and it's very interesting how each of those contractors brought a different flavor to the team. At the end of the day, though, it was a really fruitful early collaboration that allowed us to get to the kind of net zero performance that we achieved. Now, as an introduction, these were the costs in 2015 for the lower school. So consider these in 2015 dollars. And we bring up this slide only to show that the cost per square foot for this time period and this area was at the low end of schools being constructed at this time. It also wasn't a very large school, so we didn't have a lot of area to kind of spread the costs around. And the point is really that high performance really can be achieved through thoughtful design, even on a modest budget, if you have a really good collaborative team and you're willing to iterate on the problem. So the first thing that we did for all of these projects is set early energy goals and to really define what those goals mean. So for the lower school, we set an EUI goal of, an EUI meaning energy usage intensity, of 22. That was the goal that we needed in order for a future PV panel to be able to supply the building with the rest of the power it would need. We also looked at the Architecture 2030 goals, which at the time was a 70% reduction over the baseline code. We were able to look at our local energy program incentives. ETO is Energy Trust of Oregon, and they had a Path to Net Zero program that we were able to participate in and get some incentives that really covered some of the cost of the energy modeling and the passive modeling. And then we were able to get the project to be net zero ready, which means that it doesn't have the future PVs installed, but it is PV ready. It has the infrastructure and it's structured to allow PV to be installed later. The gym project that we're going to talk about also considered resilience because it would be a high assembly space and the place where the entire school might gather, both for events, but also in case of emergencies. So that project ended up being designed at a resilience category 4 level structurally, and we also considered additional resilience measures in mechanical systems. At this point, Ruan's going to talk about the energy data that we did.
Yeah, so Steffi really talked about focused on some of the data, right? And this is what John wanted to see, was the data, right? So let's talk about the data. One of the first things that we like to do, and this is what we did on all of these schools, is to really set some early goals, right? And to do that, we did some very preliminary energy modeling, and this is early in the schematic design process, where we model the building or some level of the massing of the building in the simulation software, and we run that with some weather simulations to see what kind of energy usage that building may have, right? And this chart, this bar chart of EUIs, really helps to kind of bookend where we may be able to design the building to, right? So, for example, on the far left is an existing building of this type, might be somewhere around the 75 EUI. And then you see the good or the code, where if you design this building to code levels, code minimum levels, you might be closer to a 50 EUI. And then on the far right, you'll see what the labeled as a solar resource, right? And that's indicates what the net zero energy goal is. That means on this project, we could fit a 270 kW PV array on the roof, and that's equivalent to about a 20 EUI production of energy. So we would need to bring our building's energy use down from code of 50 all the way down to about a 20 if we wanted it to be net zero energy. So we provided some good, better, best, simple scenarios where we could potentially achieve this option, right? So when we provide this kind of data, then we have to back it up, right? So we say, okay, well, what's good, what's better, what's best, how much does it cost, what does it mean? So we follow that up with some simple bullet point information on what a good building looks like, what a better building looks like, and what a best building looks like, right? So it's improving the envelope from a code to a little bit better, and then even better. So we're looking at HVAC systems, improving those HVAC systems. And then we list what is the EUI, so in case here, 48, 38, and 22. And what is the energy cost index? This is how much you're going to be paying in utility costs, electric and gas, right? So this is the good is both electric and gas. The better and best are all electric scenarios where you can reduce your carbon footprint at the same time. And then you provide some simple payback numbers. And this all, again, not very detailed, all at a rough order of magnitude analysis. And when we see some numbers like this, it shows to the client that it may be possible to get to a best, and so it leaves that option still on the table to move forward with. Right. One of the best things that I like to do when we show this data is do this climate analysis. So this is called a bin chart, and what it has is, in the vertical axis, it has hours of just number of hours, and in the x-axis it has these 5-degree outside air temperature bins. So this is a 40 to 45 degree temperature bin, and what this tells us is in Portland throughout the year there's about 1,200 or so hours that the outside air temperature falls within the 40 to 45 degree bin. So taking the overall look at this graph shows us what kind of climate we have, right? It shows us that in Portland, it's most of the time in the year, it's between 35 and 65 degrees, right? So overlaid on top of this is the color. So the orange shows us the hours that we need to do active heating, 54% of the year, and then hours that we need to do active cooling, 10% of the year, and then the hours we don't need to do anything, on 36% of the year. Now, this is based on a code envelope. Now, the cool thing is, what if we design that envelope to a passive level, right? What happens is you really increase that passive zone to 83% of the year. That means you only have to do active cooling or active heating 14% of the year and active cooling 3% of the year. So this, this is a when you see these kind of numbers, then you can start asking the question of the team, the owner, do we want to pay first cost to put in an active cooling system if you're only going to need it 3% of the year, right? Then you start to think, well, shoot, maybe not. Maybe we don't need to do that. So if we don't, then what happens? Right? So that's the next order of questions that we need to answer. I mentioned the energy modeling. All of these projects had to do at least some minimal energy modeling at the very beginning of the project to kind of inform the decisions. And these are just all three schools, just how the data over time, how we show that data, right? Some of these graphics, some people like, some don't, but either way, what this shows is in a K-12 school in Portland, this heating piece of this pie, this is showing the energy use breakdown of a building. So how much of the energy is being used for what? In this case, heating is about 30%, and it's very common in the K-12 in our climate. So that's what that shows. So the energy use in a building, 30% in a K-12 in Portland, 30% is heating, about 20% of it is lights, and 18% of it is fan energy. So what this does is it helps the design team really dive into what is going to be the most effective measures in reducing energy, right? So obviously, if you can target these big pieces of the pie and trying to reduce that, you have a better impact on the overall energy use of the building compared to if you tried to do some pump savings or cooling savings or domestic hot water. Now, we can dive a little bit deeper even. Look at this heating piece of the pie because it's the biggest piece of the pie and say, well, okay, if it's heating is the biggest piece, where does that occur, right? So we have that data. What this shows is in this type of building, a lot of it has to do with windows. So a lot of heat is being lost out the windows. And then a lot of the energy to condition the required code minimum ventilation is taking up energy as well. So those are two big items that we can work on. Selecting more efficient windows and selecting systems to more effectively condition the ventilation air. And then thirdly is infiltration or leakage into the building. So trying to design a more tighter building.
All of this comes down to trying to understand the trade-offs by increasing how robust the envelope is, making it tighter, making it higher performance windows. Those tend to add first costs. And for most projects, we have to be able to balance that by reducing costs elsewhere. And most of the time, the best way that we could do that is by completely eliminating a system. So what Ruan's energy model was able to show for the lower school project was that we could balance the increase in first costs if we could completely eliminate the cooling system, and that was a way that our first costs didn't increase by implementing these measures. For most projects, the capital budgets and the operations budgets are separate, so we can't take that into account. So while there's a great long-term payback in energy that can be poured into the programming of the projects, we can't usually consider that in our initial first costs.
Hey, Steffi, can I jump in here a minute?
Absolutely, John.
So when talking about costs, a couple things are important. One of the great things about institutional clients, I think, people often say is that we can take the longer term look and we can be willing to pay a little bit more upfront for the savings. At the same time, as a private institution funding these based on donations, and it's a big fundraising project for us, we don't have a lot of wiggle room and a lot of room to spend money, more money up front. And it's vital that our project be a success. And we measure success on a couple parameters. One is our ability to control costs. So the initial cost is very important. And also to have program success. So the performance has to be there. And so in this case, we really made it difficult, and the design team said, yeah, we want to do this. And guess what? We don't really want to pay any more money for it. And on this project, we were really able to achieve that successfully. And that was a big win for us. And in terms of performance, it's why I kept harping to Ruan, show me the data, show me the data, show me the data. Because at the end of the day, if we're not putting an air conditioning system in the building, we have to be sure it's going to work, because the best way to kill a future project is to make this one not perform well.
Indeed.
Thanks, John. So how do we do this? Well, we look to nature somewhat. How is passive cooling handled in nature? Well, it's basically handled through breezes and shade. I love this image because that lion just looks so comfortable in the shade and having the breezes on the savanna. And so we do the same basic idea. The other half of the strategy is robust insulation. How do we keep the heat inside during the months where we're creating heat, and then how do we keep the heat outside during the months where we don't want the heat? And so between the passive cooling and the robust insulation, we really took those two strategies as we designed the building. So this is an overview of 3 diagrams of the 3 schools: the lower school, the French Americans middle school, and then the athletic center. And Ruan's going to walk through the diagram, and then we'll show you an image of what it looks like.
Yeah, so this is the diagram that we've used for the lower school when we started out with developing the concept. And it really helps to visualize for everybody what the concept is, right? So first of all, passive heating, right? So when we design in a really robust envelope, walls, really low U value windows, roof, what it does is it basically traps the heat inside these classrooms, or more accurately, it slows the rate of which of the heat that's being lost from the space. It slows it down such that the heat gain from the people and the lights and the computers is enough to keep the spaces warm when the classrooms are in session. And so, but you know, as John mentioned early on, well, you know, there's no people in the buildings at night. What happens when the teachers get in there 7 a.m.? They're going to start complaining. I don't want to hear complaints, right? So, which is valid fact, right? So we do have an electric cove heater, one simple cove heater in each classroom, and that's there to kind of do a morning warm up prior to the teachers come in, and then keep the space from freezing overnight, or you know, pick up any additional slack in case the heat gain from the people internal gains didn't work. So on the passive cooling side, we have manually operable windows, natural ventilation stacks, which use the buoyancy effect of hot air. It'll rise up and leave these doghouses on the roof. And then there's a green light, LED green light, and a push button. So what this does is there's a control system that looks at outside air temperature, inside the classroom temperature, and it decides when it's optimal to go into a passive cooling mode, or when it's optimal to open the windows. So this green light will turn on, and the students or the teacher will go in and press that button. It'll open this pair of dampers here, and then they'll have to manually go open the window. Then what that does is it allows for this air coming through the window and up the stack and out. In some of the cases, we put in a small induction fan at the side of the doghouses to induce a little bit more airflow. And then in the corridors, we have some natural skylights to introduce some natural daylight into the corridors, and really big, wide open glass windows between the classrooms and the corridor to introduce that daylight into the classroom as well.
So this is what it looks like, just looking from that corridor through the big transparent window and then out through the classroom into the nature and beyond. And we've tried to highlight a few of the things that you can see, the operable windows, the cove heaters up above, window shades. There's photo cells to control the lights so that they're on occupancy sensors and on a photo cell sensor. The green light you can't really see because it's actually behind the camera, and the air vent you don't really see because it's up high, but we wanted to give you a sense for how that looked.
Yeah, one thing you'll note is you don't see a lot of HVAC. There's no ductwork. There's none of that because it's pretty simple. So in the French American school, we went a different approach because these weren't double loaded corridors. They were single loaded corridors with some, you know, these kind of common spaces we did out here, right, Steffi? And so we did more of a cross ventilation approach where we, instead of doing a stack, we allowed natural ventilation to come in operable windows, out through some acoustical louvers between the classroom and the corridor to keep some, you know, we made them acoustical louvers to mitigate any kind of acoustical transmission. And then we had these manual gang operated windows that would open up to allow for that cross ventilation feature to occur.
So this is a view looking at that common space, and you can see the classrooms on the left with the acoustic louvers up above them. They were done in wood. They were a custom piece for that one piece. Because there weren't classrooms on either side, we were able to just mostly mitigate that acoustic impact. The school just opened and then had to close due to COVID. So we don't have a lot of good data yet on the acoustic and side and the performance side of this. The idea then would be that this common area could also have a broader temperature range than the classroom. So it could be a little bit warmer during the day. And they're also right next to a forest. So if it really got warm during a couple months of the year, they could go out into the forest. One of the areas that was a big challenge was how do we gang operate those high windows on the right-hand side there. And we came up with a system that could open them all on one side, because when you have a common area, then you don't have a single person with the responsibility to open those windows like you do in the individual classrooms that we had on the lower school.
One thing you'll notice in both the lower school and the French American and the next project is exposed thermal slabs or exposed concrete floors acting as thermal mass. That was a critical element of the passive cooling to work. So the next one is the OES Athletic Center that is currently under construction. Like Steffi said, completely different from any of the others that we've done in terms of passive programmatic needs. But what we have here, this is the new addition to the athletic center, and you have the gym playing floor down below, and you have this concourse level kind of at this middle area, and the windows entry into the space is all occurs at that concourse level. There's a dedicated outside air system that provides mechanical ventilation on all three of these schools. There's a dedicated outside air system. So that system provides that ventilation air through floor grills on the concourse level, and also through some grills located behind these bleachers that provide the air at a very low velocity, so these people sitting on the bleachers aren't affected by too cold air. And then we have some perimeter radiant heat along here. And of course, we have the body heat of the kids playing and things like that to heat the space. Now, instead of those doghouses that we showed on the lower school, which, by the way, we had some lessons learned there, because those louvers on the side of the doghouse, they started leaking in water when. John, do you want to tell the story?
Sure, I'll talk about that. Yeah, we learned a couple of things. One is Portland is a mild climate, and we don't get much snow, but we do get snow occasionally. And I think it was the first winter we got a good snowstorm with blowing snow from the east, and the snow blew in the louvers, condensed inside, and ran down the walls below. So we had to solve that one. And then we also found that the doghouses really, in a couple classrooms particularly, really caught the east wind in a way that made them less comfortable. So we had to fashion covers for them that we put on seasonally now.
Yes, so we decided those weren't going to work too well at the athletic center. So we put these turbine ventilators in. In fact, the turbine ventilators got put on the Reynolds School District 3 elementary schools as well. And so and you have the operable windows at this concourse level. Now, I have to admit, when we first did this modeling, I was a little concerned because I wanted operable windows down at the playing level, right? I wanted the air to get to this playing level. Because what will happen is these windows will open, the air will come out of the windows, and it'll pretty much stay high and go out of the turbine ventilators at the top of the ceiling. But once we started doing the passive cooling modeling, what we found was that this was very effective. In fact, what it did was, since hot air rises and you get stratification occurring in this really high bay, this approach is very effective because it just took out all that stratified hot air and allowed the playing floor to cool down. So I learned a lesson in the modeling on that one too. So that was quite interesting.
Ruan, if you go back, we should also mention that the exterior solar shading on the south side was pretty critical to make sure that we kept some of the hot sun on the south out during the day. And that was something that was an added cost for the project. And we had to do a lot of modeling to make sure that we didn't do too much because it was expensive, but we had to do enough to make sure that it was keeping some of the heat gain from entering the building.
That's a good point. And we'll get into some of these different measures that we use for solar or passive cooling in a little bit. But I wanted to show a little bit about some of the details going into the calculations of this passive heating and passive cooling. Passive cooling is relatively easy, right? Basically, you're balancing heat loss. So in this case, you got these two graphs. I know it's engineering speak, but play along here. You get this horizontal line, right? And essentially how much heat the people, the lights, and the computers give off. And we assume it's pretty consistent at around 4,000 BTUs per hour. So that's a rate of heat being generated in the space. Think of it as a heater. This other line is how much heat is being lost through the envelope. Because it's warm inside and cold outside, he's gonna leave the space. And how fast that heat leaves the space depends on how cold it is outside. So this x-axis is the outside air temperature, and the colder it is, the faster the heat is being lost. So all this area here, you would need active heating to really keep the space warm. And this is with a code envelope. And so what this says is this balance point temperature is somewhere around 55 degrees. So below that, you have to do active heating. In a passive envelope, you're really slowing the rate of heat loss through the envelope to a point where this crosses this balance point temperature is somewhere around 30 degrees. So in Portland, that's quite a lot of hours where, anytime below 30 degrees, you'll probably have to do some active heating, but anytime above that, you don't need to do anything. So in Portland, that's quite a bit. And that's based on the passive envelope that we designed for this school building. Now, in other climates, we could design an envelope that's even better that could reduce that balance point temperature much lower as needed for the climate. What's also interesting is this energy use here. It shows that the heat load in passive buildings, majority of it, once you get the envelope really dialed in with good windows and walls and roof, a lot of the load is due to infiltration or air leakage. So really building a tight building was really important. Now, passive cooling is not as easy because it is time-based. There's a lot of factors going into heat cooling load. So we actually have to build a computerized model and do a annual simulation of it. So this is kind of a snapshot of what our model looked like. We did the worst case classroom, like Steffi mentioned, in the lower school. We just did the southwest facing upper classroom because that was the worst case in terms of heat cooling load. In the French American school, we did a multiple areas. So what this shows is, for that space, we took different scenarios. We just labeled them G1, G2, G3, I1, I2, I3. And this shows how many hours in these different temperature ranges. So this is, above the blue is really temperatures above 80 degrees, right? So when we showed this to, well, I don't think we showed this to John. I hope not. I think this was internal, and we kind of said, okay, obviously these three are not going to work. You got way too many hours above 80. Let's not even show that to John. Let's focus on these I1, 2, and 3 measures, right? So that's what we focused on. And then there's a heat map that we showed that this is, I think, for one of the G options that show hours, days of the year, and when those temperatures occur during the year. Now, these are some of the scenarios that we looked at. So in the G2 scenario, for example, these are some things that are really important for passive cooling. So natural ventilation during operating hours. In this case, we did no external shading for the lower school because we couldn't fit that into our budget. So we had to make it work without external shading devices. Night flush, using that dedicated outside air system. Exposed concrete floor, it was a 2.5-inch thick. And then, of course, a natural ventilation shaft with a fan assist. With the eye approach, all of that, right? And then we added a 60-degree Fahrenheit ventilation air. So we did a little bit of cooling through that ventilation air. And that's because we weren't able to do the shading. So it was like it was a optimization of cost and operation. And because we weren't able to get the shading, we had to do a little bit of cooling through the ventilation air. Again, just these are options, option I, heat maps, and we were able to really show that we had 4 hours where temperatures got to 80 degrees, and that was sometime in September at 2 and 3 o'clock, 4 o'clock in the afternoon. And this is the information John requested. He said, well, if it's going to be 80 degrees, you're going to have 4 hours of 80 degrees. When is it going to occur? And so we had to provide that data, and this is what it was. And this was enough data for John and the steering committee to become comfortable moving forward with this concept. Of course, then they came back and said, oh, by the way, what happens on during a heat wave? So we took some historical data and we ran a week of 100-degree days, above 100-degree days, to see what happened. And that came out okay as well. Then we did this is an example of what we did at the French American School. No need to get into a lot of details, but what you can see is we did all kinds of different areas rather than just that worst case classroom. And as Steffi mentioned, what that allowed us to do is really optimize the design for the various parts and areas of the school, rather than design the entire school for the worst case classroom, which we did at the lower school. Then we did the athletic center. You can see the kind of the graphics and how we display the graphics kind of change over time. But here where we did the normal case analysis is current climate data. We showed that between 75 and 80, about 3.8% of the occupied hours. Above 80, only 2 hours a year. And then we kind of had this graph. We dialed in on some of when these occurred. It showed additional data. And again, the steering committee came back and said, well, what about climate change? So we ran the same model with a 2050 climate projection and showed that 75 to 80 was like 13%, and then 12 hours above 80, and this was worst case. And we ran this with 500 people in the gym with the 2050 climate projection and no overhang, like that exterior shading on the south facade, which Steffi had talked about. So this was good enough for us to move forward. And by the way, we did get that shading on the south facade, so that helps us immensely. So next, we're going to kind of get into the details of some of this, the envelope, because that's really important, and the air leakage. This is showing some of the blower door testing that was occurring during the construction. One of the first things we recommend doing is a mock-up. So before building the main building, doing a mock-up and testing that mock-up for all the details that were designed into the project. This is that very first project that we talked about, was the Earl Boyles. We did a mock-up of that. One of the things we learned was we had specified fluid applied vapor barrier, or fluid applied weather barrier. And this is constructed in the middle of winter, and the sheathing was wet. The wood sheathing was wet. Contractor came back and said, we can't apply fluid applied on wet sheathing. And so we had to go back to a peeling stick. In this case, a Henry Blueskin, you can see that. And that worked fine. We just had to go through and, they created this, tested it, blower door tested it, found some leaks, went back, retaped some of the edges, things like that, and ultimately came to a design that worked. You can see that, this is the Z clips here from the sheathing out, and some, this is the, where the cladding would be connected. And I know, John, you had some lessons learned with the fluid applied membrane at the lower school too, right?
That's right. We ran into the same situation. We were getting to this point in the wet months, and we realized that there just wasn't any way we could apply it, and we switched to Blueskin as well. Yeah,
but it worked fine. Yeah, so here's the wall construction detail on the lower school. It's the R40 assembly. This shows the entire envelope, actually: R50 wall, R50 roof, R40 wall, U.28 windows, air filtration of 0.2 CFM per square foot of wall area. And we achieved this through double pane fiberglass frame windows, by the way, not triple pane. We couldn't afford triple pane. But yeah, so we have an 8-inch stud cavity with obviously batt insulation there, and then a 4-inch layer of continuous rock wool with the Z-clip, and then a lightweight cladding on the exterior. Of course, the weather barrier in there too. And that's been the pretty much the wall construction detail that we've used on almost all of these projects. Here's an example of, this is the lower school. Compared to Earl Boyle's, you can see it's, the Z-clips weren't the thermally broken type here, but we were still able to get a really high performing wall detail thanks to hackers' efforts in kind of really detailing the wall. And you know, we did a blower door test, and like I said, we were hoping to get 0.2 CFM per square foot, and that's what we had modeled in all of our passive cooling models and energy models. But we ended up performing a lot better. So we ended up around 0.07 CFM per square foot. So we're really happy to see that. So John, you've been tracking some energy use.
Sure, I'll talk, and just to step back a minute, you know, I talked before about how important having the system perform as designed was, and so we felt it was a good value to invest in first the mock-up, which we found, the contractors found incredibly valuable. It was a place where they had to coordinate the work of 4 or 5 different subcontractors, and based on their experience with the mock-up, they actually changed and modified some processes, and I don't know if they changed any of the specs, but kind of the order in which they did the work, they came to a much better understanding of that. And then we felt it was important to do the blower door test too. The one thing we did learn though is we didn't really plan that far enough in advance, and doing the test required a certain level of finish on the interior as well. And so the bottom line is, when we did it, it was a little late. Had it not, had the results not been good, it was a little late to actually react to it and fix the problems. Fortunately, the mock-up really identified the issues. The envelope was built well, and the results were good. I think this this graphic here about the energy use is, I think, pretty incredible to look through what was modeled and what our experience is. You'll notice that all the months are very close with the exception of the summer. And that was one of those conflicts of assumption, let's say, that it didn't dawn on us to compare notes on summer use of the building. PAE assumed like, oh, this is a school, they operate 9 months a year, that means they're shut down during the summer, very little energy use. We, on the other hand, we said, oh, we've got a big summer program, I'm sure they know that, and well, they didn't. And so they modeled a closed school. We've experienced an open school. But you'll see that except for July and August and some of June, after a couple years, the actual experience is really close to the model, which is really encouraging and gives us really a lot of confidence in looking toward the future. The other thing that I'd say, and this is a little more qualitative and anecdotal, but Ruwan spent a lot of time showing you the modeled temperature performance of the buildings. And while we're not collecting data the same way we are in the case of energy use, I can tell you that I monitored that pretty closely, and that for the most part, the temperatures we're experiencing in the building are really close to what's modeled. And again, that gives us confidence to move forward in the future with our next project. Okay. One of the interesting things we've learned, and I think we knew this going in, but a passive system means active interaction. So passive equals active. In order for this system to work at its best, the cooperation and participation of the occupants is really important. The sequence of operations is really pretty simple. But teachers are working with kids all day and they're not focused on the ventilation system in the building. And so even a simple system can be a little bit of a challenge. In this case, it's one, notice that the green light is on. Two, if the green light's on, first go open the windows. And remember, you need to open all the windows because they all need to be open for the next piece to work, which is when you go and press the button and the louver's open. But at the end of the day, it can be a little bit complicated. And what we really learned is education is important, not only at the beginning, but as we go through, we'll forget the process. As new occupants come into the building, they need to know how the system works. So in a lot of the cases, we still have occupants that are at the really basic level, which is, it's kind of warm in here. I think I'll open the window. And go much past that. But the ones who are more bothered by it are more motivated to learn and reach out and say, how did you say that worked again? And we're able to offer that retraining. So finally, to wrap us up a little bit here, here are some of the takeaways that we've touched on in this presentation. One, the lessons learned. Some of those are positive. Some of those we learn, we shouldn't have done that way. And the doghouses, of course, is the biggest example of a design piece that didn't work out very well. We reacted to it. We have a solution that works, but in the future, the design has changed too. I know I learned that it's, on the one hand, really important to push the design team to provide the modeling that we need, but at the end of the day, when we do that, we can trust in it. The results, the performance has shown us we can trust the design modeling. Integrated delivery was hugely important to us on many levels. To get to an assured budget for us, it's really important to have the contractor and subcontractors on board early. But the early collaboration between the boots on the ground and the design team really helped us hone in on a solution that would work really well for us. The owner buy-in is really important. We talked about that. We were motivated to work in a direction toward not only less expensive operation, but also we were motivated by just minimizing our ecological footprint. At the same time, we had to bring along a lot of donors who may have had different assumptions. And so together we worked on that and we came to an acceptable solution. But again, it put the pressure on the design team to really prove the concept. Use what you have. I am amazed still when I watch the building in operation to see the immense impact that occupancy of rooms has in terms of providing heat. I'll watch a building or a classroom slowly warm up until it's occupied and then notice in the next 45 minutes the temperature really takes off. We took advantage of our climate. Portland has a mild climate and was really, I think, in the sweet spot for applying this particular solution. We also took advantage of our site. We have a sloped site, which allows us to have on-grade entrance and exits at 2 different levels. It gave us a more vertical building, which is a little more efficient in terms of ratio of volume to skin. And so we took advantage of all those things. Just mentioned the passive versus active. Again, the real learning point there being occupant education. And at the end of the day, feedback loop too. We monitor the building carefully, fiddle with set points. We are monitoring the performance of the building. You know, the testing during construction was crucial too. And I think in the big picture, the feedback loop that says, okay, this is what works and this is what didn't work, and feed it back to the design team so it can impact their future designs and inform their future designs. So all in all, a great project. All these takeaways for us meant that we were willing to enter the next project and be willing to use the same type of solution, different application, certainly, but we had the confidence to move forward and know that we can have a successful second project using the passive approach. And then finally, this is just a fun picture. our curriculum really stresses inquiry and self-motivated education and project-based education. And so having a construction project going on our campus is a real boon. The kids love it. We often have the design team or the contractors visit the classrooms to answer questions, and you can imagine the awful lot of questions they get. And in appreciation for all the hard work and the good show going on, the kids were encouraged to write notes to the construction team. And here are just a few examples of some of the cute things that they did, and it really meant a lot to the contractors to get these notes. So that's what we have today. It's been really fun to be with you and to describe our projects. And hopefully there'll be a Q&A after this, and we really look forward to being able to answer questions. If there isn't a Q&A, again, go to the course outline, I think, that has contact information for us, and we'd be happy to answer questions if you reach out to us. Steffi, Ruan, you have anything to add?
No, you summed it up great. Thanks, John.
Okay.